Okay, welcome to screencast number 5, part 1, experimental designs. So we're splitting this screencast into two parts because there's a lot of material to cover. The first part is on experimental design, so these are true experiments where you're actually manipulating something. And the second part will be on non-experimental designs where no manipulation is taking place. And so there are basically three types, and I'm grouping them together here into two categories: experimental designs and then quasi-experimental designs and single case designs. But we'll talk about the last two together. So what are the essential characteristics of an experiment? First of all, you have to be comparing at least two or more groups. And the group that receives the treatment is going to be your experimental group. The group that doesn't receive your treatment is your control group. Sometimes you can have comparison groups where they're actually receiving an alternate treatment, and these are sometimes also referred to as control groups. And so that's basically the setup for the groups that you might have in an experiment. Second, you need to be manipulating the independent variable. This is a subtle point, but it's important because things happen in the real world without us intervening, and so manipulations are happening due to policy, due to new instructors being involved, due to all kinds of different natural things. But in order to be a true experiment, the researcher has to actively manipulate the independent variable. So you have to introduce a treatment and a control, or do something to manipulate the people in your study. And this independent variable, the one that you're manipulating, is called your treatment variable or your experimental variable. The third thing to be classified as an experiment is that you must use random assignment. This is essential to be classified as a true experiment. Random assignment of some kind has to take place. And random assignment means that every participant who comes into your study has an equal chance of being exposed to the treatment or the control. And so what you can state based on that is that the groups that you create are essentially equivalent, because there was no systematic reason why one group would differ than the other if random assignment is used. So random assignment sounds pretty easy, but there are actually quite a few ways to implement it. And the reason we might do it differently is to add more control and to increase our chances of getting equivalent groups at the outset of our experiment. We're trying to avoid this idea that one group differs in some way, shape, or form than the other. And if you're dealing with small sample sizes, just by random chance alone, even though you've implemented random assignment, you may end up with differences. And so the idea is that there are other strategies you can employ to ensure that you're getting equivalent groups at the outset. So the first way to control for pre-existing differences is random assignment. Essentially, with a large enough sample in terms of who are taking part in your study, you should end up with equivalent groups if you employ random assignment. But if you're worried about the fact that somehow one group might end up look different than another, especially on a particular variable, you may move to the next level, which is randomized matching. This is where you match your participants based on some important variable that you're measuring before you've introduced any intervention. Maybe it's on their level of experience. So you try to find two people in your sample who have the same level of experience, and then you randomly assign those two people to the two groups. And therefore, you're ensuring that when all is said and done, the groups that you end up with have the same level of overall experience, and you haven't somehow biased one group to be more experienced versus another. This is, again, a strategy to help deal with this idea that you may have a smaller sample and you just want to make sure 100% that your groups are equivalent on a very important variable. The third strategy is to use homogeneous selection, and this is just to hold the variable constant. So rather than study highly experienced and highly inexperienced people, you would pre-select your sample based on how much experience they have. So you're only dealing with students who have a lot of prior practical experience, for example, to take part in your study. You would leave out the people who who don't have any experience, and therefore you can definitely say, once you randomly assign that selected group of people to the treatment and the control, that they're going to be equivalent on that variable. You can also build the variable into your design, and so you can measure it and then use an analytic technique or compare your experimental groups across that additional variable. So, for example, you have a treatment and control. You measure the sample's level of incoming experience. You classify them as either having high or low. You've essentially created 4 groups. You've got the people who have a high level of experience, who've been assigned to treatment and control, and you've got the people who have a low level of experience assigned to the treatment and control. And then you can start looking at all the differences that emerge based on those 2 variables and their interactions. So you can also just use subjects as their own controls. So this is the idea of having a pre-test prior to receiving the treatment or the control, and then also having a post-test. So what we're saying there is, when we compare performance post-treatment, we can compare it against the baseline, and we can show that there's either been improvement or no improvement. And then there's analysis of covariance, and this is just an idea of, again, building a variable into your design. So analysis of covariance is for non-categorical variables, so a continuous variable such as age, where you have a range of values that a person can exist on, and essentially, rather than creating groups, you're going to control for that continuous variable, and you're going to say, when I control for this age variable, do I get different results? So there are 2 classes of experimental designs. There's the weak experimental designs and then the strong experimental designs. And sometimes in education, we are in the world of weak experiments. So it's important to know about these, because they can be essentially all we have at our disposal in order to study what we want to study. But they are weak because they don't do as good of a job controlling for threats to validity. And what I'm talking about here is our ability to interpret the results causally. So can we make the inference that the treatment is actually causing any improvements we see? So the first type of weak experimental design is the one group post-test only design. And essentially, you have a group of people, you treat them, and then you measure them. Obviously, without having a pre-test baseline, we don't really have any basis for saying there's been an improvement. We don't have any comparator to say that people who didn't experience the treatment showed less improvement. And so this is a very weak design in terms of saying that the treatment is causing anything. Then we have a one-group pre-test, post-test design. This is getting a little bit better. We have baselines now, and we treat our individuals, and then we measure them after the treatment. The post-test only design with non-equivalent groups. So we've introduced the comparator. So we've introduced a control group, and we've introduced an alternative treatment. So in this version here, you've got a treated group and a control group. They're both measured at the end on the outcome variable. In this one, we have a treatment group and a second treatment group, and then both measured on the outcome variable. And what this does is it allows us to show any difference over and above people who haven't been exposed to the treatment. But you can see here there's been no random assignment in any of these weak designs, and therefore we have no guarantee that the treated group and the comparator group or the control group are equivalent. So then we move into the strong experimental designs. And the first one is random assignment, pre-test, post-test, control, or comparison group designs. So this image right here, that doesn't work. This image right here shows the pre-test, post-test control group. So you can see we've got XT, which is our treated group, and we have our XC, which is our control group. They were both measured prior to being exposed to the treatment or the control and after being exposed. And then at the beginning, we see that they were randomly assigned to groups. So we've got equivalence of groups, we've got pre-post, and we've got our comparison. This is really one of the strongest designs you can expect to get. And then all this image here does is say, instead of having a control group, we have treatment 1 and treatment 2. So same benefits of this design: random assignment, pre-test, post-test, and we have a comparator in the sense of we have a second treatment being employed. So very strong design to make causal claims about the effect of a treatment on the outcome variable. Then we have something called the randomized matched participants pre-test post-test design. And again, with the two figures here, we've got one version where we've got treatment versus control, and another version where we have treatment 1 versus treatment 2. So in this case, we've got the pretest, but instead of randomly assigning prior to the pretest, we're going to measure people first, and then we're going to match based on scores on the pretest. And then we're going to ensure that based on that pretest, we've got equivalent groups. So we're going to match high people with high people, low people with low people, and we're going to randomly assign those pairs of individuals to treatment or control, and then we'll measure the post-test. So this is just giving you a little more control than the previous design because you're ensuring equivalence on the outcome measure of interest. Then the same idea is happening here, except we've got treatment 1 versus treatment 2. So then we move to another type, which is the randomized post-test only control comparison group. So this is slightly less effective than the first two designs. And the reason being is we've eliminated the pre-test measure. So we simply have random assignment, treatment or control, and then we have our post-test measure. So our outcome variable is measured at the end of the experiment. And then this version of the figure shows the same design, but where you have treatment 1 versus treatment 2. So we've eliminated the pre-test measure, and therefore we've got a weaker design. So then we move to randomized matched subjects, post-test only control group, control comparison group. And so this image here shows a version where we've matched on some attribute, not the outcome measure of interest, something like maybe experience. I talked about that as an example before. We've measured their experience, we match on experience, then we randomly assign to treatment and control, and we measure our outcome variable, which is not experience, something else, performance, whatever it might be. And we've introduced some improved control because of the matched random assignment, but again, we're missing that pre-test. And this would be the same, actually this image should be T1, T2 instead of T and C. But you get the idea, it's the same pattern of all the other designs we've seen. So matched random assignment, treatment 1 versus treatment 2, that should be a T2, and then measured on the outcome variable. So one thing that all of these designs that I've covered so far, 1 through 4, fail to do and fail to account for is the potential for the introduction of an effect due to being pre-tested. So we've talked about how you can actually increase your chances of doing well on the post-test if you've seen the pre-test. And so what this design does, this whole 4 rows of description here, is it says we've got 4 groups. We've got 2 groups who receive a pre-treatment measure. First we randomly assign them, then we pre-test them, and then we treat the people who were randomly assigned to treatment and control the people who were randomly assigned to control, and then we measure them at the end of the experiment. But as a part of this experiment, we also had a group of part of our sample was randomly assigned to a treatment condition without a pretest and a control condition without a pretest. And so now we can compare to see if introduction of a pretest actually changes the effect of the treatment. And so we get to control for that, or at least quantify the effect of having been pre-tested on any improvements in the outcome. And so this set of 4 rows here describes the same exact setup, except rather than treatment and control, we have treatment 1 versus treatment 2, treatment 1 versus treatment 2. So essentially we have pre-tested group, non-pre-tested group. Within those 2 groups, we're randomly assigning to be treated with our primary treatment and then an alternative treatment. And then we are measuring all of those people on the same outcome measure. The final experimental design to speak to is factorial designs, and this is where you have more than one independent variable. So one of them might be manipulated, and the other would be some kind of attribute variable like gender, male and female, for example. And what you're trying to do is investigate whether or not there are differences in the effect depending on whether you are male and female. So this is what the design looks like. You end up with the 4 rows, the 4 groups. So you have one group which was randomly assigned to to treatment 1, but they are all males, for example. So on the x variable, we're going to call that the attribute variable. We're going to say that T1 is male, and we're going to say that T2 is female. So these first 2 rows are all males, and all the males were randomly assigned to receive the experimental treatment or the alternative treatment, and then they were measured at the end. Then all the females, same thing, were randomly assigned to either receive treatment 1 or treatment 2 and measured at the end. So you can see here we're able to investigate in this set of rows if there's an effect for females, and we can compare the results we get for the females to the result we get for the males. It's actually very similar to the Solomon 4 groups design in the sense that we have 4 groups. Each row represents a group. The first 2 rows are people who received a pretest. The second 2 rows are people who didn't receive a pretest, and we're going to compare the results of our experiments for this subgroup, the ones who didn't receive the pretest, to this subgroup, the ones who did receive the pretest. Is the treatment effect stronger or weaker depending on whether or not you received or did not receive a pretest? So the Solomon 4 group design is a factorial design where one of the variables was pretest or no pretest, and the other variable was the experimental variable, treatment or control. Going back to the factorial design, 4 groups again. One of the variables is an attribute variable. Males, for example, taking care of the first 2 rows. Females taking care of the second 2 rows. And we're going to look at the effect of our experimental variable, Z, on the outcome variable for males only. Then we're going to compare those results to the results to what happens for females only. And so this is the factorial design. One manipulated variable and another attribute variable. And another way to represent these is like this, and you've probably seen this in research articles. They'll often say, I have a 2x2 design with 2 independent variables, so each number in this depiction represents a variable, and the value tells you how many levels there are. So there are 2 variables in this design that have 2 levels. So the first could be male and female, or it could be pretest versus post-test. Sorry, pretest versus no pretest. The second variable has also got 2 levels, and this could be the experimental variable, which would be treatment versus control, and 2 levels. So in this design, 2x2x2, there are 3 independent variables, and they all have 2 levels. And so, once again, we could have gender, we could have introduced the pretest versus no pretest variable, and then we could have our treatment and control. So you see we end up with 6 total groups, and we can start looking at effects across all the different combinations of those variables. So the same logic applies. This would be 3 variables. The first variable has 2 levels. The second variable has 3 levels. The third variable has 3 levels. And finally, 2x2x6. There are these kinds of designs. So imagine that this third variable, which has 6 levels, is grade level. So in a lot of educational research, we may look at differences in the effects across all the different grades. So grades 1 through 6, for example. So to really bring this home, it's good to see how a factorial design might look like when you have actual data. And so what this is just a simple 2x2 factorial design where we have 2 variables. The first one is learning method. There were 2 types of treatments, cooperative and individual. And then the second variable is this attribute which we measured prior. And we didn't manipulate, we just measured their ability. So we measured and we categorized them as either high or low levels of ability. And so what we've got here is our 4 groups. So we have our cooperative high, our cooperative low, and we have our individual high and our individual low. So we could actually calculate the mean for this group of people, the mean for this group, the mean for this group, and so on. 4 different means. And this is the raw data we would have from our experiment, and we would do an analysis based on means that looks like this. So here's what the data would look like if we actually calculated the averages. And just to complete the example, the power of this type of design is to say that, okay, I can look at the effect of the treatment in the low group, and I can also look at the effect of the treatment in the high group. And so if I were to take the difference between cooperative and individual, in the low ability students, we see that there's a 30-point difference. So the cooperative education students had on average, a 30-point higher score. If we then look at what's happening in the high level group, the difference between cooperative and individual type education is only 10 points. So there's a much weaker effect. So that's really interesting to see that depending on the level of ability of the students, the intervention is having a differential effect. Okay, so now we're going to move to quasi-experimental and single-case designs. We'll cover what quasi-experimental designs look like. We'll talk about how well each controls for internal threats to validity, and then we'll look at some single-case experimental designs. So essentially, the difference between quasi-experimental and true experimental is that we haven't been able to randomly assign. So as soon as you haven't been able to randomly assign, you're in the quasi-experimental world. We're still manipulating, we're still actively manipulating the independent variable, but we are no longer able to randomly assign. We have pre-existing groups. So the first type is a simple non-equivalent control comparison group design where we've implemented pre-test, post-test. So our treatment group is some classroom where we went in and tried out a new method. Our comparison group is another classroom where we expect there to be a similar type of student, but we have no control over that, and we don't introduce them to the new method. So this is the classic treatment control version, and this is, say, where you have 2 alternative treatments, so the primary treatment and then maybe the traditional intervention. Then there's something called interrupted time series designs. So this is where you're measuring at baseline over and over again this group of people. Then at some point you introduce your educational intervention, say for example, and then you follow up and measure them on the same outcome over and over again. It's like a repeated measure of the same group leading up to the treatment, and then a repeated measure following the treatment. And where this comes into play is situations where programming dictates that this is what will happen in terms of an intervention. You know, at some point they will be taught in some way, shape, or form. So prior to them being taught, let's just measure how well they are doing at certain outcomes we expect to be affected, and then let's follow up with them and see how they perform after they've been affected. So this is allowing you to compare following a treatment to pre. Then interrupted control group time series. Obviously the weakness of the first design is that there's no comparison group. This is where we have, again, 2 existing classrooms. In one classroom we have the ability to, intervene and provide a new treatment. In the other classroom, they're getting the old traditional model. But prior to intervening, we measure them at baseline over and over again, and then we follow up with, again, a series of measures of the same outcome. Regression discontinuity design is a very complex design, and it's essentially where you have a pre-test, or it's not really a pre-test because we're taking advantage of something that's happened in the real world, like a decision about who is going to get the treatment and who's going to get the control. So say, for example, we determine that we're only going to intervene if you score below a certain average on the pretest. So you will get special intervention if you have a low score coming into our class. So we're going to measure you coming into the class on some related outcome that we expect you to be improving on by the end of our course. And then depending on how well you perform, you're either going to get treated or you're going to get the control. So this was all decided on prior to us coming along as researchers. So we did not set the cut score, but we did not determine the policy that these people would be treated. but we can take advantage of the data that results and investigate whether whether there's an effect of treatment compared to the control group. And so it's really hard to see what this looks like without looking at some data. So let's look at this image here. Imagine that we measured people on the pretest. So we have a range from 0 to 100. And all of the people who received a score lower than 50 ended up getting a special intervention. And so then we've measured them on the post-test. And this is the scatter plot of the data that resulted. So here's your pre-test score versus your post-test score. And all the people who, in the blue, below the cut score on the pre-test, received a treatment. All the people above the score, above the cut score, did not receive a treatment. And we get to see, okay, is there a differential effect? So do people who received the treatment end up performing any better than people who didn't receive the treatment? And there's a lot more that you'd have to read up about on how to do this analysis, but essentially when we're analyzing this data, we're only really looking at people who are really close to the cut score, because we know that, and this is a really interesting artifact of measurement, is that when you measure someone, there's error involved. So if you're really close to the cut score, it's almost like you've been randomly assigned to receive the treatment versus the control. We know that anyone who got 49 could have very likely got 50 or 51 and then been put into the control group. And so what we do with regression discontinuity designs is we only really analyze people who are close to the cut score, and we look to see, is there a difference at that cut score? So I'd encourage you to, if you're interested in this, and this type of design is really powerful for large data sets where you have access to large amounts of information, large amounts of data, pre-test scores, decisions, and then post-test scores and treatments happening in between. But if you're someone who's interested in large data sets and analysis in that regard, regression discontinuity design is a very powerful way to make causal claims about intervention effects. So the last one is this counterbalance design with intact groups. So again, we've been dealing with intact groups this whole time. So imagine we've got 4 classrooms now. And at time 1 of our experiment, we are going to treat them each with a different type of treatment. So treatment 1, treatment 2, treatment 3, treatment 4, and then we're going to measure them. But there may be an ethical implication here that treatment 1 is supposed to be better. So ultimately, by the end of the experiment, everyone has to be exposed to all the different treatments. And so you go through this process of alternating which treatment you're exposed to and then measuring the outcome variables. So group A gets exposed to all the different levels of a treatment, and you can assess order effects too. You can talk about, well, if you received this order of treatments, is there a difference in the effect of the intervention than if you received this order of treatments? And so this is a way to control for counterbalance for order effects. So essentially, sometimes the order in which you receive treatments or are exposed to things in experiment can impact the effect. So you may want to have part of your group exposed to one order and another part of your group exposed to another order in order to investigate whether there's a change in the effect depending on which order you received. So I'd refer you to the text in order to find out more about this, but there's a section on how well do quasi-experimental designs control for threats to internal validity, and essentially you're going to want to assess or look at whether or not history, maturation, testing, instrumentation, regression artifact, differential selection, all of these threats to internal validity, how well do these quasi-experimental designs control for them? So I'd refer you back to the text to really understand all of this, because it's too much to cover in a short screencast, and this screencast is already quite long. So single case experimental designs. This is the ABA idea where you measure baseline prior to intervening, then you intervene, and you measure multiple times after the intervention has been introduced. And then you take away the intervention and you see, does the person go back to baseline, or is there any effect, long-lasting effect of the treatment? And then you finally reintroduce the treatment and then follow the person along. And so this is a single case, a single person is involved in the study, and you're looking for patterns that the intervention has improved baseline. So you've essentially got a series of pre-test, post-test experiments happening here, or time series. So you've got prior to intervention a series of measures, and then intervention at the sixth observation here, and then follow-up measures. So this is a powerful design, and it can be useful for demonstrating behavioral effects. And then another alternative to this would be multiple baseline design. So this is just the idea that you're measuring more than one thing at a time, and you're following them, introducing the treatment, and then seeing how these different outcomes, so it's like you have multiple outcomes that you're following, are affected by the introduction of the treatment. And then finally, this is the changing criterion design. So you essentially measure baseline, you change the criteria, you change the level of the treatment over time. So in this example, the treatment criteria was the allowable cigarettes per day. So in the first few days of this experiment, they were allowed to have 16, and then 14, and then 12, and so on. And we see that the actual number of cigarettes smoked decreases depending on this level of the treatment. And that covers off experimental designs. The next screencast, which I'll start right away, is non-experimental designs.